everyone. Welcome to this week's C3 AI DTI seminar. My name is Matthew Wu. I'm a postdoc at Berkeley ECS. I'm co-hosting this semester seminar with Professor Shankar Sastry from UC Berkeley and Professor Srikanth from UIUC. C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthrough with large-scale societal benefits. This semester seminar has a special focus on incentive design and learning for societal systems. And we have confirmed a line of truly fantastic speakers for this series, so please be sure to follow the whole series with us. If you missed the talk, you can find the speaker information, talk abstracts on our website. You can also subscribe to the newsletter and YouTube channel and follow the talk and the slides and the talk video for the past event. So please be sure not to miss our event. Today, it is our great honor to have Professor Michael Jordan here to share his research on dynamics-informed blending of machine learning and game theory. Professor Jordan is the Pei-Hong Chen Distinguished Professor at the University of California, Berkeley. His research broadly covers machine learning, optimization, control theory, and computational biology. Professor Jordan is a member of National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences. Sorry, someone raised the hand. I don't know. Okay, sorry for this. Stop. Professor Jordan is a member of the National Academy of Sciences, National Academy of Engineering, and the American Academy of Arts and Sciences. He's a former member of the Royal Society, and he was a plenary lecturer of the International Congress of Mathematicians in 2018. Professor Jordan has received many prestigious awards, including the Alf Grenader Prize from the American Mathematical Society, the IEEE John von Neumann Medal, the IJCAI Research Excellence Award, and David Rumelhard Prize, and as well as the ACM-AAI Alan Newell Award. Without further ado, let's welcome Professor Jordan. The talk will be in total 15 minutes. For the audience, please use the Q&A feature to submit your questions, and we will ask your questions on your behalf. Thank you, Professor Jordan. The floor is yours. You can start sharing now.
All right, thanks very much. Let me do the sharing and get going. All right, I'm very pleased to be invited. The framework of this talk, I think, is really appealing, kind of big picture, where's technology going?
Sorry, Mike, I think you're sharing the, not the projected.
I'm not sure sharing correctly. I'm okay now. We play from start. Is that looking good?
Yeah.
All right, thanks.
Thank you.
Help me if there's any glitches along the way.
Sure.
But we all know they do happen. All right, let me do a full screen. Okay, so I'm going to give a somewhat unusual talk today. It's going to be more about vision, but you know, visions, how do they come to one? And they really, I don't know is the short answer, but I kind of started to have one at some point, and I want to sort of give a little bit of a personal history of how I started to see the work I'm doing and how that leads all the way into research questions. And so it's kind of the kind of talk, maybe if I had been a grad student or a young professor, I would have liked to see someone give. You just see these great papers and these great results, and you don't know how it ever emerged. So I hope to give some sense of what's beneath the hood when you work in research for many, many years. So you can sort of see machine learning, game theory, and dynamics, and certainly that's where I'm at. I'm in this kind of tripartite blend of economics, computation, statistics, and so on. So let me, though, kind of step back and move into my home field of machine learning. It's really a blend of computer science and statistics with a lot of support from surrounding fields. It's become really, really a thing. And it's surprising to what extent it's become a thing. The technology over the last 10 years, deep learning and whatnot, is really gradient descent with large bags of parameters. It's that kind of way of thinking's been around for quite some time, and it's called pattern recognition. And what we see is a lot of people trying to use very high-powered pattern recognition for all kinds of problems. with some successes and lots of notable failures. And it's not really clear what's going on at some level. You can't use pattern recognition to solve all the world's problems. So what's left? What else should we be working on? Why isn't it enough? And so on. So I want to highlight the decision-making side of machine learning, which is just as old as pattern recognition. Really goes back to people like Blackwell and Ken Arrow and others in the 50s. And it's just as important. And I want to argue that it's not been paid nearly enough attention to. All right. So just to show the standard picture of a neural net there, this requires labeled training data. You have input-output pairs, and it's become dominant. It's become a commodity. There are lots of real-world use cases you can think of, but actual productivity gains are lagging. Definitely nothing like, say, search engines or recommendation systems, even, which was an early form of pattern recognition in terms of billion-dollar productivity gains in the economy. Now, I think really there's a reason behind that. And so I want to give you an example, very concrete one, of going into your doctor's office, maybe in a couple of years, and the doctor sits you down and is in possession of the world's biggest neural network trained on all the world's medical data, everything. Everybody's history, so on. So suppose various boundaries have been surmounted and we have such a neural net. So the doctor sits you down and measures 100,000 things about your body. Maybe he takes your genome, measures your height, your weight, your blood pressure, and so on, but many, many other things. All right, that $100,000 dimensional feature vector goes into the neural net, and out pops some, let's call them predictions, patterns that have been recognized. And so one of those outputs is the heart disease output. And let's suppose that if that number is over 0.7, based on all the historical data analysis, you're in danger of having a heart attack. And so suppose yours is 0.701. What are you going to do in that moment? Are you going to treat this in any sense as a decision? And I'm going to argue no. The first thing you're going to do is start to open up a little dialogue with your doctor. You're going to say, well, first of all, I need to understand the uncertainty here. I need an error bar. What's the error bar around that 0.701? And I don't mean just a little Gaussian error bar or some maybe simple bootstrap or something. I mean, what data was this based on? Is this old data? Is it recent data? Was it, done with people like me? And you're going to ask counterfactual questions. What if I were to exercise more? What if I were to get a second opinion? What if and then you're going to remember things about your past that you hadn't remembered before. Oh, my parents had heart disease, or, as a kid, I had asthma. And so on and so forth. And the doctors, you're going to bounce that back and forth. And so all kinds of new data is actually to become relevant in that moment. And that's what real decision making is about. It's not just taking all the past. And you realize at that moment, the neural net did not contain all the world's data about healthcare. It can't. The relevant data becomes relevant in the moment of conditioning on making a particular decision because a particular result has happened. And so you really do counterfactual analysis with the doctor at that moment. You think through all the other options, you think about things that could be different. And in some sense, you're doing more data analysis on top of the original data analysis. And it's this loop that you go back for just before you actually finally make a decision about what to do. All right. And I would argue this is true of most consequential decisions. It's a loop, it's a dialogue. There's considerations of provenance. Where did the data come from that make me think this way? Relevance, counterfactuals, and so on and so forth. Many, many open, hard problems that, people, database people have looked at provenance, but just for kind of like banking problems. What about medical problems? What's something mean? What's it mean to be relevant? All right. Now, that's, of course, just a tip of the iceberg. We never just make one decision in isolation. We're always making whole sets of decisions over different timescales, even years. And we're doing them in groups, and we're doing them across networks, and we're all linked up. Even planetary scale, the response to a pandemic is lots of individual decisions made on lots of data flows based on lots of partial information, hopefully bringing, upping the social welfare. And so I think that's the right level of analysis. An AI system that sits down with one individual and you have this little data analysis, it's so limiting, and it's dangerously limiting. It's going to lead to lots of uncalibrated errors, and they're going to be consequential ones when they start to go into the real world. All right, so just to give another little vignette here to help convince you this is an important way to think. Consider classical recommendation systems. These are, yeah, all of you know what they are. You go to Amazon, you get recommended things based on your own past history. So it's a recommendation system based on pattern recognition. Hugely successful in industry. It's changed e-commerce, but very much on the prediction side. And if you start thinking about this as a decision-making system, you're going to run into all kinds of difficulties very quickly. So if you start recommending movies to people, and your system is really working and you recommend it to lots and lots and lots of people, you could easily recommend the same movie to 100,000 people in a given day. I'm sure that happens at Amazon or Netflix every day. Is that a problem? Well, no, because there's no scarcity in the world of bits. You can copy the bits as much as you want. All right. Similarly with books, you can copy books quickly. If you recommend the same book to many, many people, no problem. But now what if you go out into the real world and you start recommending things to people? Like, for example, if I build a recommendation system for restaurants based on the commodity software of matrix factorization, and everyone in the city is using it, I could easily recommend the same restaurant to 10,000 people. I'll create a line down the street of unhappy people. I could recommend the same street to many drivers, and we all have kind of heard of this. We create congestion by having closed loop recommendation systems. If I recommend the same stock purchase to large numbers of people, I can destabilize the market, and so on and so forth. So these are all situations in which you're interacting with the real world. In the real world, there is scarcity and there are stability issues. How do you fix this? And I think here Silicon Valley has been very limited in their thinking. They sort of say, well, it's just load balancing. I'm not going to ever recommend 10,000 people to go to the same restaurant. And you say, well, how many people are you going to recommend? Well, I'm going to cap it at 50. And then you say, well, which 50? And they say, well, I know a lot about people. I know based on the browsing history that Mike Jordan likes Szechuan restaurants, or Shankar Sastry, likes, Southern European dishes or whatever. So I'm going to send them to the appropriate restaurant. And first of all, this is ridiculous. It's going to invade privacy. It's going to incentivize the invasion of privacy. It's not going to be real. You're not going to know in the moment what restaurant you want to go to. And there's no way you want Mark Zuckerberg to know. So we need to build a market instead. So the right way to think about this is a two-way market. It's not a platform that makes recommendations. There's consumers on one side, there's producers on the other side. They're all learning as they go. They're learning about their preferences. They're communicating, they're making bids. And you need a platform that structures all of that. So it's a matching market in the economics language, but it's one where the preferences are not known a priori. And whether there's a long time frame in which these preferences are being learned is part of the matching process. So I hope you sort of see that there is already a major real world challenge. It's not solved at all, even in academics. We don't know how to build matching markets at the scale of hundreds of millions of entities where preferences are not known, and so on and so forth. All right, so I actually just briefly want to allude to the fact that I've been involved in a project in the real world. There's a company called United Masters, which is doing what I'm about ready to say. Which is, there's a broken music market in the world, really, but especially the United States, where huge numbers of people are making music. It's being streamed out there, and advertising and subscription models are being used to make money, but they're being used to make money for the people who are doing the advertising and the streaming, and not for the actual musicians. And little bits and pieces are flowing back to musicians, but really it's not a real market, and you can't control your destiny and so on. So you don't want to think about this as a platform like Spotify that streams. You want to think about it as a two-way market. I've got some producers on one side, huge numbers of 16-year-olds who are making great music. And I've got some consumers on the other side, lots of other 16-year-olds who are listening to music all day long. And if I start to think about building a healthy market and having some transactions, I can start to see how money and value can flow across this network without any advertising whatsoever. So United Masters is doing this, and I just want to allude to my friend and colleague, Steve Stout there, who's a major impresario in the music world. United Masters, if you go to that website, you'll see kind of what I mean. There's over 1 million musicians on the who have signed on with United Masters. They are making music. Their music is being sent to people like the NBA. If you go to the NBA website and listen to the music there, you will hear the music from United Masters artists, and they're being paid for that. So this is a healthy new market. Behind the scenes, it's machine learning, matching, econ kind of principles being done at scale. Very ad hoc, I must say, because we don't really have the principles yet. But I just want to give you a sense of the real world consequences of thinking this way. All right. And in fact, a lot of the dialogue about AI has been, we got all these great pattern recognition systems. They're so good, they can replace humans in all kinds of tasks. Oh, that's a problem. We're going to, damage the labor market and so on. There's some truth to all that, but it's also just the wrong way to think. Instead of trying to replace humans by being superhuman, or understand how to, put a human thought in the computer. Instead, think about mechanisms that'll complement humans, that will maybe build markets, that will do things that humans don't do very well, so they can be yet more empowered to build yet bigger connections among each other. That's the way you supercharge things like economic value. All right, so we really have to reset a little bit. The AI world, and I've gone on and on about this perhaps too much, but it's just been focused on this classical AI vision of let's do vision and speech and natural language. And if we can do all that really well, there'll obviously be great things coming out of that. There haven't really been great things coming out of that. And I think the great things that'll come out is if you think about a systems point of view, about a kind of planetary scale economic system based on data flows, that's really what we're trying. That's what we actually are building in real life. But we got to, as academics, think more about this. All right, so let's turn to being academics. Are there problems at these new interfaces? Well, there's millions of them, and a lot of them are old. David Blackwell would recognize everything on this slide, but they're old and they're still, and they're new. The new issues have arisen, new platforms, new hardware, new everything, new data, but they're not solved. And so just general relationships among optima, equilibria, and dynamics, many unsolved problems. There's a whole program at the Simons Institute focused on this. Multi-way markets in which agents have to explore to learn their preferences. I'm going to get into this a little bit, but I've already alluded to the need for that. Sort of bandit algorithms meet markets. Large-scale multi-way markets in which you view the other side via recommendation systems. So recommendations aren't just a one-sided thing. I want to be recommended restaurants want to be recommended clients, and all that. On both sides, there's recommendations that help structure a market. How do you incentivize people to share information? Big open problems there. How do you do mechanism design where you're learning all the preferences? You don't assume they're known a priori. All kinds of robustness, and I don't just mean robustness of neural nets. I mean robustness of really the economic kind as well, and the statistical kind. And then many of the discussions about privacy, fairness, and social good are all really good, but a lot of them are just, well, the neural nets are broken in this regard. We got to fix the neural nets. But really, there's a much broader set of issues at play. These are big social problems. Of fairness doesn't mean like treating everybody the same. It means respecting people's utilities, finding out about their utilities, and trying to then balance people's utilities, like in a more economic way of thinking. That'll already won't solve all the world's problems, but it'll already kind of head us more in the right direction. All right, so we need new principles. I don't think this is going to be a gluing together. I think we're going to need some brand new principles to build healthy learning-based markets that are stabilized over long stretches of time. And I want to emphasize that long stretches of time point. One of the elephants in the room with current AI pattern recognition systems is they don't work over long stretches of time. It's called distribution shift or whatever. They work over like a day. And if you've got huge numbers of engineers, you could keep fixing it day in and day out. But that's not the real world. You want systems that'll work over, days, but not only that, over years, really, like markets do. They adjust, they adapt, and so on. All right, so we're missing this kind of way of thinking, I think, and we've got to worry about this. Okay, so I'm going to return to that slide. That came out of order. So let me now transition to another part of my talk. That was kind of the personal history of how I got to where I am. But what do we have to contribute? Are there new ideas that'll help us trying to tackle these problems as we work towards these new concepts? So I'm going to argue there's going to be some new mechanism design principles in this talk, and then there's going to be some new dynamical systems ideas in this talk, and some new statistical ideas if I get there. And so I'm going to start with the dynamics part of it, because I think that's often where it's neglected. We talk just about the equilibria and the preferences and so on. But I think in these really large scale systems, you're probably never going to actually be at an equilibrium. Everything is always shifting, and it's about the movement that really matters. So I want to give you just a brief 5-minute background on what we've learned about dynamics in the last decade. This is a particular paper with colleagues Chi Jen and others. There's a version now in the JACM of this work if you want to see details. And this is all about saddle points. Saddle points bring in kind of non-local geometry. They bring in dynamics that is kind of non-trivial, non-convex. And we've made more progress than you might think about this. And of course, saddle points occur also in equilibria kind of problems. And so the kind of dynamics we're talking about here and the geometry is definitely relevant to kind of bridging between machine learning and game theory. All right, so there's a picture of a saddle point. And kind of for the machine learning optimization side, we want to escape saddle points. We'll then transition in a minute to the game theoretic side where we want to approach saddle points. But if you want to escape saddle points, it's hard. And in particular, think of the saddle point living in a million dimensions, which is the current kind of state of the art, large scale neural nets. And so there might be a few handful of directions in which you can escape the saddle point. Most directions you can't. You go back up a hill, and you don't know those directions a priori. And gradients are kind of near zero in this regime, so they're hard to get out. So this seems like intractability. And so even if you don't necessarily hit a global optimum, which we know is NP hard, the question is, if you start in an arbitrary place in a space, are you going to get stuck near all the saddle points for long periods of time so that you really can't have a real-time system? And that, like I'd say 5 years ago, was definitely a big concern. All of our theoretical results either were suggesting exponential time to escape saddle points, and that is actually true for deterministic algorithms, or very high degree polynomial times in certain special cases. So anyway, we started working on this. And so if you start asking about gradient-based algorithms, if you have no local, singularity saddle points and so on, we have rates, 1 over epsilon squared, accelerated rates and so on. You get down to the bottom very quickly, and that's been hugely important. But if you run those same kind of algorithms on this sort of surface, you can get stuck for large amounts of time. The question is, how large amounts of time as a function of dimension? So we want our rates not just to be a function of time or accuracy, 1 over epsilon squared, but as a function of dimension. All right. In the convex case, gradient descent is independent of dimension. That's an amazing fact about gradient descent. It's part of the reason it's so successful. But what about the non-convex case? Okay, so this paper, you can now look at all the details. This summarizes it here. Here's our rate up there. The rate is 1 over epsilon squared. Epsilon is an accuracy criterion. There's a Lipschitz constant, and initial distance is the optimum, and those are all the constants. There's no hidden constants except the dimension dependence. That's why there's a tilde on that O. But we now figured out the dimension dependence. For a particular algorithm, it was polylogarithmic in D. So it's not exponential, it's not even polynomial, it's actually logarithmic. And so this paper, established that and made it really clear why high dimensional gradient descent, this is a stochastic form of gradient descent, is actually quite viable and quite feasible. So what is happening here is this is a rate to arrive at a local minimum, okay? So there might be huge numbers of saddle points. In fact, we know problems where there's one global optimum, but a rings of saddles. And so the whole problem is the saddles. All right, but even if there's huge numbers of saddles, turns out you escape them, you move past all the saddles and arrive at a local minimum in a number of iterations, which is 1 over epsilon squared. And that's kind of amazing because the rate for gradient descent in convex problems, in which there's none of those complexities, is 1 over epsilon squared. And the only penalty we're paying here is that polylogarithmic in D, which is not bad at all. All right, so that paper and many others in this literature have really made us feel we really made progress on non-convex problems. All right. So once you make that kind of progress, you start asking about, is this the best? Are we done? Is this the fastest we can go? Have we kind of figured out the essential aspects of this problem? And so now you start looking at lower bounds, and the Russian school, led the way, a couple of decades ago or several decades ago, and discovered that there are lower bounds to be had, and there's these accelerated algorithms which achieve the lower bounds, but they've been a bit of a conceptual mystery. And another piece of progress in the last 5 years has been to uncover some of the elements behind that mystery by going to continuous time. And in some sense, almost all the work I'm going to talk about today and sort of the dynamics part is all done in continuous time. And the whole challenge is to actually then discretize correctly, okay? And some sense this shouldn't be a surprise, because when you go to continuous time, you can actually talk about acceleration. It doesn't really mean much to accelerate if you're hopping along a discrete set of points. What's it mean? You hop faster? Well, that requires an underlying topology to support the idea of being faster. All right. So long story short, in this other line of work, I want to mention, just highlight it. Again, there's lots of papers now. This was with Andre Wibisona and Aisha Wilson. Their thesis here at Berkeley was on this topic. And also Mike Bettencourt was an early person working with us. We brought in continuous time into optimization, and in particular, understanding lower bounds and accelerated methods via variational, Hamiltonian, and eventually symplectic perspectives. All right, and so I'm going to just tell you kind of the upshot here on one slide. These algorithms that are accelerated in the Nesterov sense, that have these faster rates and kind of usually put together 2 gradients rather than just 1 gradient, or maybe have two equations rather than one. They have a little bit of an oscillatory flavor to them. We found one Lagrangian that captures all of them in continuous time. We call it the Bregman-Lagrangian. There's also a Hamiltonian version of this. It has got a Bregman divergence in there. It's got a few kind of degrees of freedom in these exponential time constants, but it's basically a Bregman divergence minus the function you're going downhill on f. So it is a Lagrangian. It's kind of a kinetic energy minus a potential energy. You pump all this into the Euler-Lagrange equations, and out pops at the bottom of the slide there a single master equation. That's the differential equation for acceleration in a wide variety of settings. All right, and the further exploration of this Bregman-Lagrangian, and now many people have been doing this, reveals there's a lot of geometry being captured by this equation. Okay, so without getting into any details, this line of work allowed us to see if you go into continuous time, you can actually understand how geometry impacts how fast you move in certain spaces, and this applies to convex and non-convex situations. Okay, so I'm going to go back here to the slide that I was out of order just really quickly. Okay, so a bunch of lines of research have come to the perspective that continuous dynamics allows us to understand these gradient-based algorithms. We're able to understand when and why they don't work. We're able to actually understand phase transitions in rates in the continuous domain. All right, and you could now formulate new algorithms in the continuous domain in many cases in brand new ways. And that last bullet there, I just want to highlight some work with Michael Muhlebach here. If you want to, again, look on my homepage, you'll see papers where we've been taking this perspective of continuous time into constrained optimization. This is a brand new project over the last year, but long story short, constrained all of the machine learning work is almost all unconstrained, right? And Nesterov. But what if you want to do constrained optimization? And usually constraints are put in as in the kind of the position space. You have barriers, you have projection operators. But what if you put constraints into forces or velocities, more of a dynamical perspective? So if you move a certain direction, you get a force pushing back against you. Well, that can be done in this continuous time Bregman-Lagrangian time to framework, and the work with Michael has done that. And now you can have dynamical systems that are solving constrained optimization problems. So I think that's opening up a whole new perspective, and not just optimization, but also things like equilibria finding and so on. So I just wanted to highlight that. Now, the next to last bullet was important. So we do all this work in continuous time. We get these rates, and we get optimal rates. They meet the lower bounds in continuous time. But there's this oddity, which is that we need to get back to discrete time to actually have accelerated algorithms that actually achieve these lower bounds. And if you discretize these differential equations in a dumb way, then it turns out you will lose the fast rates. Okay, and dumb way can actually be something like Runge-Kutta. All right, but it turns out that symplectic integrators actually could provably retain the fast rates, and so that became a theme for us as well. Symplectic means you kind of took the geometry seriously. And let me just briefly say what this is. It's such an important concept in applied mathematics, and it's, I think, going to be increasingly useful for others. When you normally integrate a system of differential equations, you have a vector field, and you arrive at a point in the vector field, you have a little vector leaving that, and you take a little step along that vector. That's basically the integration procedure. Symplectic integrator is a whole different idea. It's due to Poincaré and others, Hamilton. You arrive at a point, and you have a triple of vectors there. And imagine that triple flowing along the vector field, and it shears as it flows. A triple of vectors defines a little volume element. And if you ask that volume element stay constant, that says that a certain determinant is staying constant. And that's a polynomial constraint on your dynamics. And the question is, can you discretize so that that constraint still holds? Okay. And the answer is yes. It's a constrained problem, and they were able to solve that. Why is that useful here? Well, if you keep that volume element kind of constant, you have a very stable discretization. You can take much larger steps in the discretization of your differential equation and still stay stable. And that idea that you can take larger steps is what ties this to acceleration and to optimization. Okay, and so we have a sequence of papers kind of making that into mathematics. Okay, so now I'm going to go back to this paper, which came out of order. All right, so with Eric, who was co-advised with Shankar Sastry and me, he came into my group about the time we had done this work, and he says, well, why don't we think about using symplectic ideas, in terms of Nash equilibria? He'd already been working on this. Nash equilibria are hard. You're down trying to find saddle points, not avoid them. All right, but they're a special kind of saddle points. And simple gradient dynamics are known to, to oscillate and even to diverge in situations like this. All right, so here's a little picture over there on the right. The little three blue X's there, above and below, those are Nash equilibria in this two-dimensional space, i.e. it's a saddle point, but it's a special kind of saddle point. It's aligned with the axes because one agent wants to go down, the other agent wants to go up, and the agents are aligned with the axes. Okay, so those are Nash equilibria, and you would like to have gradient-based algorithms that approach those Nash equilibria. And as I alluded to, that's a challenge. And things like extra gradient algorithms kind of can do this, but it's non-trivial. So Eric designed an algorithm which does approach those Nash equilibria, and others have designed such algorithms. But there's a thing in the middle there, that star is actually a saddle point, but it's tilted relative to the axes. So it's not a Nash equilibrium. So game theoretically, you want to avoid it. These other algorithms that actually are able to not oscillate will approach that saddle point because they don't know any better. They don't really kind of recognize there's been a tilted saddle point. So they happily go and approach that. This new algorithm is that little red curve there. It approaches that non-Nash saddle point. It sort of sniffs out that it's tilted and it moves away and then eventually approaches to a Nash equilibrium. Now, why is this relevant to what I was saying before? Well, the actual algorithm that does that is written down here, where we called it local symplectic surgery. And basically, it's canceling the symplectic component of the vector field. The previous work showed you that if you exploit the symplectic component, you get the accelerated algorithm. So for optimization, symplectic is good. For equilibria finding, symplectic is bad. So if you cancel the symplectic component, that's what allows you to avoid these non-Nash points. All right, now this is still a very interesting active area. This particular algorithm does this, but it requires calculating Hessian. So this is a second order algorithm. We tend to prefer first algorithms, and kind of an open problem is, can you do this with first order algorithms? Okay, that was the first maybe 2/3. Let me now go more into the economics blended with machine learning, kind of with some of our dynamical tools at our disposal. We're now kind of ready to tackle hopefully interesting classes of problems when we start to bring in incentives and we start to bring in agents who have their own strategic desires and so on. All right, so I'm going to, again, very, very quick here. These are all papers you can read if you want details. This is work with Lydia Liu and Horia Mania, students with me at Berkeley, where I had been talking in these vague terms about these restaurant recommendation systems and why wouldn't it be nice if we had two-way markets and you could do exploration at the same time you structured the market. And Lydia and Horia really were the ones who turned this into a real project and made mathematics out of it. And so I want to briefly allude to what they were able to do here. So you all know what a multi-arm bandit situation is. It's a learner who's sampling various arms, various choices, and getting rewards back. And over time, trying to figure out what's the best arm so they can get the maximal reward. And if you do this in a smart way, kind of blending exploration and exploitation, you will get high reward, but you'll also not miss the opportunities for good rewards of unexplored arms. And so that's called low regret. So there are optimal algorithms in terms of their regret, like, for example, the upper confidence bound algorithm. Upper confidence bound just forms it's a statistical approach. It just forms a confidence bound on the mean reward for each of the arms after the experiences. And then it picks the arm that has got the highest upper confidence bound. It's the one that you're maybe the most uncertain about, or it's the one that is seeming to get the highest reward. And by picking the upper bound, you get both the exploration and exploitation. Okay, so that's a brief introduction to the machine learning side of this project. What about the economic side of this project? Well, we were looking at matching markets, and so this is Gale and Shapley and Roth and so on. They considered bipartite matchings where you have buyers and sellers. The buyers have preferences on the sellers, and the sellers have preferences on the buyers. So college admissions would be kind of a classical example. All right, Here you've assumed you know the preferences a priori, right? If you know that, you can now write down these algorithms, for example, the Gale and Shapley algorithm, which sort of iteratively forms a matching, and the matching needs to be stable. And they have a criterion, which is that there's no there's no one buyer and one seller who would be happier off switching with another buyer and seller than they are in the current matching. Okay, so if that does not happen, you're stable, and that's the criterion of success for the algorithm. Right, but in the real world, lots and lots of problems. We don't know our preferences. The buyers do not know which seller they prefer. Restaurants, I don't know which restaurant in Shanghai I prefer. I've never tried them. I need to try them out a little bit before I decide. And this is true in lots of real world domains. Okay, so what happens if both the buyers and sellers are experimenting and trying to explore? All right, well, now you get an algorithm context. You have a model in which there are competing agents. So suppose there's now two players and they're both trying to find which arms they prefer, and the rewards might be different for the arms for each of them. But they're at some point going to conflict. If here agent 1 and agent 2 both pick arm 2, only one of them is going to get a reward in our model. So we're modeling congestion. All right, suppose that the bear gets the reward. All right, why did the bear get the reward? Well, it's because arm 2 also has its preferences back on the left side of the market. So it prefers the bear for whatever reason. It may also be learning that. All right, so the human sees this and says, oh, I see, I liked arm 2, but I see that the bear likes arm 2 also. And when I pick the arm 2 and the bear picks it, I lose. So I better explore some of the other arms more than I otherwise would. And so that last statement suggests I'm going to have a bigger regret. I'm going to have to explore more than I otherwise would in this competitive situation. All right, and so we analyzed this and calculated the regret. And it turns out the regret is actually not higher in this situation in the number of iterations. It's still logarithmic in the number of iterations. It's higher in terms of a constant term, which reflects the amount of overlap between the agents, the bear and the human in this case. All right. So that's a first, I'm going to skip the details there. That's a first project on matching markets and bandits. In a second project with a bunch of people here at Berkeley, Mina, Alex, Yixi, and Jacob, we started looking at the more, let's call it realistic real world problem where you have transfers. Okay, so this is more like the Uber platform where you've got riders and you've got people wanting to ride, and you're going to find a matching, you know, one person's going to go in one car, but you're also going to pay. The rider is going to pay the driver. And this again allows Uber to be kind of a two-sided market. It doesn't have to do advertising. It just takes a transaction fee. All right. So you can view this as an econ problem and do your mechanism design. But again, you're not necessarily going to know a priori who prefers what. You're going to not know how much to pay. You're going to have to work all that out. So we need to think about two-sided matching platforms in which we have to find market outcomes that align with preferences, that have incentive compatibility, that have transfer utilities, because that really opens up the range of possible matchings to a much broader class. And we've got to be stable, and we ought to be able to learn all of this. All right, so those last two criteria actually come together. Stability for econ people is generally a 0-1 kind of quantity. You're either stable or you're not. If you're not, then you can't say much. The market will unwind. If you're stable, that's good. As more of a statistical or control theory kind of person, I want models in which there's a gradation of stability. There's a perfect stability, but if you move away from that, there's a quantitative notion of how unstable you are. Why? Well, then we can get gradients that return us to stability. And we can also structure learning algorithms that learn with such an object, with such a criterion as like a Lyapunov function. Okay, so in this project, that's what happened. We're trying to find equilibria, and we're trying to find a Lyapunov-like function that allows us to structure finding those equilibria. And so one way to think about this is that there's this notion of a price of anarchy, the difference between the equilibrium and the optimum. If we'd like to minimize the price of anarchy and not just characterize it, we need a Lyapunov function. So we need to make it quantitative. All right, so the picture now becomes, it's Shapley-Shubik, but we have all these question marks, you know, what are my preferences? So the Uber domain is not so clear. I mean, I prefer to get from one place to the other, but the restaurant domain and so on, it becomes clear. In general, you're going to need unknown preferences. And then the payments have got to be structured based on the utilities. So it's all linked up. All right. And so here at the end of the day is a particular proposal in this paper, which is a quantitative measure of instability. And I'm not going to get into this at all, just to say the tau A there is a payment. It's the transaction. And then you have the matchings there and the utilities UA. And the last important part of this is that maximum outside of all the brackets. The maximum, this is over subsets of agents. All right. And this is critical. And this gives it more of a kind of a cooperative game theory flavor. So this is kind of like a Shapley value. You're looking over subsets of agents. And so that kind of gives this kind of serious stability and blended with this quantitative notion inside of the brackets there. Okay, so it's a little hard to interpret, and that's kind of one of the reasons I don't want to get into it directly. But if you take the dual of this, that becomes much more interpretable. And it kind of has this kind of what if kind of flavor if you look at the dual. And so you can work with either the primal or the dual for interpretability and also algorithmically. So this paper then takes that further and learns equilibria for matching markets from bandit feedback, kind of turns this into a exploration exploitation idea using this primal dual formulation of matching with transfers. Okay, so I've really gotten through kind of the main meat of the talk. Now I have one little section left and I'll be able to finish, I think, on time. Let me just say, I think this is a particularly important piece of work. It is really bringing together a lot of the elements. There's kind of algorithms being done here at scale, learning mechanisms, and mechanism design all being brought together. And I think this is really just the beginning. Let me also allude to the fact that we're not alone here. I want to emphasize that. In fact, there's a Simons program and all this kind of thing. And there's really large numbers of people, I think, are relative to the number of people doing AI neural nets, it's like, 1/100th, but large in some meaningful sense, working, agreeing that these are areas to be working on and are making lots of progress on it. I think it's a really exciting time to be a researcher to see this new set of issues being worked on. Okay, let me mention one more project and then I'll stop here. This is again with Eric and again with Shankar, who was a co-advisor for Eric. And then Tiana Zernich, who's also a grad student now at Berkeley, co-advised by Moritz Hart. And so this is about feedback together with learning. So it brings together some of the things, but really kind of getting now into the incentive part of it. That's kind of what I want to finish, is with taking seriously the notion of incentives. They've kind of been hidden in the rest of the talk so far. And so you kind of all know this, that if you if you put predictive models in social situations, you'll elicit strategic behavior from people. So if you ask them to fill out a form on how healthy they are, well, they will pretend to be more healthy than they are, so they get a better rate from their insurance company. The insurance company knows this, so they will, try to make it harder for them to cheat. They will make, you have to show that you exercise a lot or whatever in some way. So maybe it's one mechanism that's been proposed is you opt in for the insurance company to measure how much your cell phone moves around during the day. It's kind of a proxy for how much exercise you get. And that, of course, incentivized people to start making devices that move cell phones around automatically during the day. So that's going to happen all the time. And this is called Goodhearts Law in economics, that if you make a measure that people know is being used to measure them relative to some outcome they care about, they will game the system to make that measure, to change that measure. It'll become less and less useful over time. Okay, so in general, we're going to have a situation where we have strategic agents who want a favorable prediction, and we've got a decision maker who's got a problem to solve, like give people loans or services, and needs to kind of figure out how to price things. So in the statistical setting, we are going to be building models from data. The agents are providing the data, then we provide a predictive model. And in some sense, we give that model back to the agents. Now, we may not give the whole details of the model, but we may be, for legal reasons, required to tell them what kind of model we're using. Maybe I'm a bank and I have to tell you I'm doing logistic regression or something. And there needs to be some recourse if you don't like the answer. So there's going to have to be some openness. All right, so this goes back and forth, and it becomes, what's called in economics or game theory, a Stackelberg game. It's a sequential game. There's a response on both sides. Okay, and so clearly, there should be some good equilibria, and ideally, there's a good equilibria for both sides. We can't just focus on the decision maker to make money or the agents to be happy. We got focus on both sides. All right, so in fact, Mortart and others sort of wrote some early papers on this, and identified this as Stackelberg game. Lily Radliff has been working on Stackelberg games. It's kind of again an emerging topic. Nash equilibria, I think, are a fun toy model to work with, but I think in many real world problems, it's the Stackelberg, which is the more important one. Okay, so the question we looked at is who's going to be the leader and who's going to be the follower in Stackelberg games, in these particular kind of statistical Stackelberg games. Okay, so classically, you assume the decision maker is the leader. They have all the power, they have the computers and the data. All right, and so that's what many games are. They're built to be the decision maker announcing some scoring system and then updating things and kind of controlling the whole game. All right, we're going to look at an approach that actually allows both sides to be the leaders, and there's a choice. So here, the agents are kind of providing lots of, the central agent is updating more slowly. So when would that ever happen? Right, well, the decision maker can be slow relative to the agents in problems like college admissions. The college is going to use some model to decide who to admit, implicit or explicit, and they're not going to change their model after every applicant. They're going to probably keep it constant for a few years, right? And then the decision makers will best respond to that, right? And so that game is very much of that flavor. The other kind of example is what we see more in the IT world, like YouTube. They will adjust their model immediately after they get some clicks. Why would they do that? Well, arguably they have the opportunity to do that. They can make more money somehow. They can make a better model and they can make more money. But it's actually known that this situation is actually not favorable to the strategic agents. It's a bad equilibrium for the strategic agents in general. And so can we actually analyze this and look at which is best in this modeling situation? All right, so let me finish with a kind of a teaser result. There's going to be two theorems on this page. So the first one is that by tuning the update frequency appropriately, the decision maker could drive the dynamics to a Stackelberg equilibrium with either order of play. So the decision maker can be the leader, or the decision maker can say, oh no, I'll be the follower. And they do that by just simply adjusting the frequency of updates. Okay, so we got this new tuning knob to achieve different equilibria. All right, now then here's the surprise, which is really in some ways a new result in game theory, which is that in several standard statistical settings, say logistic regression, it turns out that both players prefer the equilibrium where the strategic agents lead and the decision maker follows. So like the college admissions example. All right, so this is a bit of a surprise that we know the strategic agents are going to do better if they get to lead. They do badly in the other case, but it's actually surprising that the decision maker, in fact, actually does better in the case where they follow in these statistical modeling kind of Stackelberg games. Okay, so I hope that's an interesting teaser for you to give a little flavor of how, there's going to be surprises when game theory meets statistics. It's not going to be just statistics or just game theory glued. There's going to be new phenomena. I mean, if you know some game theory, you know that it's often very surprising what's happening. And some of the worst case results are really quite worst case. And you often kind of wonder, well, what if this was not so worst case? What if the agents were learning and being a little more cooperative and there was data involved? And I think the short answer, we don't know, but we sense that there's lots of new phenomena and interesting things that will happen. They're not so worst case. Okay, I'm going to skip this last part. I've run out of time. Let me just say with Winshow and models, we've been working on auctions, kind of the ultimate partial information incentive thing, and working on making them robust. Because if you're going to be learning auctions from data, which has become a thing, you have to worry about people being adversarial and providing bad data and all that. And so we use tools of robust statistics to structure auctions and not lose too much revenue. And if you're interested, we have a paper on that. The short answer is yes, you can do that. Let me skip that and turn to the end. Yeah, so let me just finish with this slide. I'm going to pop all the way back to the top level. What is happening in our era? And I don't think what's happening in our era is that AI is succeeding. And it's certainly the classical dream of AI, of human thought in the computer. It's a great thing to think about. It's a great thing to even try to do. But it's not really clear where it leads. It doesn't really, why do we need computers to be smarter than human or compete with humans? Not so clear why. It's also not what's happening. It's hard, but there is something happening, which is short of that, which is much more interesting in many ways, I think. It's a new system science emerging that has humans in the inner loop. So just like chemical engineering emerged in the 40s and 50s, before that, there were principles like chemistry and fluid mechanics and quantum mechanics. So you knew how to do things at small scale, but people started thinking, well, what if I did, chemical processing at huge scales? What would happen? And they tried it. And of course, some factories didn't work. They blew up and so on. And principles were worked out that allowed you to build factories and understand it. And that changed our world. Same thing with electrical engineering. There were previous scientific principles and then an engineering field emerged. I actually think that's exactly what's happening right now. We have proto principles of algorithms, control systems, statistics that are, decades or hundreds of years old, but we're hacking them together in these systems and not thinking about the social welfare, worrying about problems that arise after the fact, and not really understanding what we're doing. But we are building world-spanning, systems, and different from the previous ones where it was about electrons and protons and neutrons. It's now about values and decisions and people's preferences and people's lives. So I think it's probably the most exciting, interesting form of engineering ever to develop. And we're only in the very, very beginnings of it. These previous ones took decades. I think this one's going to take decades as well. All right, so I'm going to finish there.
Thank you, Mike. Thanks for a great talk. I'm going to open the floor to the participants, and if you have questions, please post it in Q&A or to the chat. I think we already received one question related to the first part of the presentation. I see one of the challenges of decision makers is how to evaluate trustworthiness of this model. There are new models like explainable AI to potentially support this point, but I'm wondering if we really know how to measure trustworthiness of these complex models to help decision-making process. So this is a question from.
Yeah, it's a great question. So I don't think I really ever said you need to measure trustworthiness, and I'm not sure I believe that's actually possible. Okay. If someone wants to be duplicitous and all, I don't know what their true value is. They tell me something, I don't know any better. So I really do think you have to take the econ point of view. Think about contract theory. I have a principal and an agent, and there's an asymmetry of information. And I really want to incentivize them somehow to give, a good answer that's useful for some other social context. And I've got to think through how to structure that. Now I also do want to do some measurements of some kind. I don't want to just assume that I've structured the game and the mechanism and everything is now incentive compatible. That's only going to go so far. And so you now need to take a machine learning perspective, I think, where I'm going to gather a bunch of data, say, from a bunch of people, and they're self-interested, and they may send me adversarial data. They may send me good data. I don't know. And I can't measure that. I can't look at the data and say this is adversarial directly. All right, but what I can do is I can do leave one out kind of things. I can take in, 4 people's data and try to do some prediction task with that. Then I could add a 5th person's data to that and see if I get a lift or if I do worse. And that kind of leave one out thing allows me to assert that that person sent me bad data, and notice that it's data in the context of a particular task and in the context of other data providers. And without those contexts, you can't talk about it. We have a philosophical conundrum. What does it mean to be good data? So this kind of test and, A/B testing, or if you will, kind of perspective will allow you to start to assess things that are happening out there. But that also only goes so far. So it's really this blend of a good mechanism and some kind of verification. And again, I think these are really hard problems. I don't think we're there at all. I don't think our current tools, if you just error bars and mechanisms and verification machinery, solves these problems. So I'm glad you asked it, but just want to say that it's going to require some new blends of these things.
Thank you. We have another question from Lyndon Yuan. You have mentioned game theory, mechanism design, and matching markets. What do you think of welfare economics, another big area of microeconomics?
Yeah, a great question. Let me just make clear that I'm not an economist, but I'm trying to become one. It's like when you're learning a language. At some point I didn't speak Italian, and then later I did. And that opened up a path. I'm trying to learn economics more. So I have a proto background and just that's what all of us are, especially for the students in the audience, be brave and jump into a field and learn about it. So I'm learning economics, and so I've learned a lot of, I've learned certainly mechanism design and auction theory and contract theory even more and more, and it's fun for me because I know a lot of the mathematics and I can sort through the books. And welfare economics, I'm certainly aware of. Labor economics, obviously behavioral economics and so on, vast fields. And it's daunting, but it's just as daunting as when I learned statistics or when I learned control theory. And so after a year or two, you learn enough. And if you have good colleagues, and ask them. So I'm really not answering your question, but just to say that the whole reason I'm doing this is kind of for social welfare reasons. I'm not trying to help Google and Facebook make more money off of advertising. A lot of people from my field who went into, industry with econ sort of interests, that's what they did. They built better auctions, second price auctions for advertising. And I explicitly tell in my group, I say, that's not what we're going to do. We're going to maximize social welfare. We're going to worry about welfare. And we're also going to be social scientists who actually go out and talk to real people and not just assume that algorithms solve everything. And so, of course, this is now not just my group. This is sort of everybody, I think, in our field. But just to say, yes, embrace your local economists, talk to them, learn about them, but embrace for even broader social scientists, legal people. This new engineering field I'm talking about emerging is not just engineering. It's not a STEM thing. It's a law thing and a social science thing and a very broad thing, just like in some ways chemical engineering and electrical engineering were as well, but even more so.
Thank you.
Right, so if you have something more, if you want to teach me more about welfare economics, there was something that triggered that question in your mind, send me an email. I'd love to hear.
Thank you. We have another question from Carl Edwards. Do you have any thoughts on the use of topology of understanding representations of these systems?
Yeah, again, very vague thoughts, but very, very present in my mind. So most of the work in machine learning has been very local, gradient things, and in statistics is very local. If you get enough data, you're around some optimum and you're 1 over square root of n from the optimum and you analyze all that. Taylor expansions everywhere in sight. It's very, very clear that kind of differential topology, some algebraic topology and all are a very powerful tool going forward. You already see some of this in game theory. Fixed point theory, Brouwer theory is all built on topology. And it's kind of, as a mathematically inclined person, this intrigues me that we're going to be using more and more topology. The saddle point stuff I told you about, there is an element of topology there, of differential topology. And that theorem we proved about that Pauli or algorithmic is actually really a theorem in differential topology. It turns out we proved that using probability theory, however. Kind of cheating, and well, not cheating, but using probability theory. And probability theory allows you also to get at topological ideas. So again, maybe for the students in the room, learn some more topology, especially differential topology. And it's not just about manifolds. It's really about the kind of the local geometry of, million dimensional spaces or 100,000 dimensional spaces and how that structures best response or, algorithms.
Yeah, thank you.
Again, if you have something more direct to teach me, I'd love to hear about it. But definitely the word topology is on. Let me just say another piece of mathematics that I think is very really relevant here is, and many people know this, but variational inequalities. It encompasses optima as well as equilibria, as well as markets, and their algorithms for solving variational inequalities. And I think a lot of our continuous time perspectives and stochastic perspectives already have, but will continue to help out there.
I have a question. It was a great talk, by the way. Thank you.
Thank you.
And I guess in many economic systems, they are dynamical systems. I mean, I guess if you're computing Nash equilibria or Stackelberg equilibria, you could do it for a static system, but the dynamics comes in the algorithmic aspect of it. But the system itself could be dynamic, where, there's some state and you're taking an action and this action changes the state. So that data, unlike normal machine learning, the data itself is affected by your actions. Of course, reinforcement learning is a very, very specific example, but I'm talking about it in terms of markets and economics and so on. So is there some work in there, or are there interesting problems there? What are your thoughts?
There absolutely are. And I think you know about some of them already. Just to say, a lot of the 25-year-olds are working on those problems. The older people like me are going a little more slowly. But there are lots of papers on Markov games or MDP kind of situations with incentives, with mechanism design. You will see a couple or three on my homepage if you look at my publications, but they're all due to my really ambitious young students. I think Tianyi Lin is an example. Zhuoran Yang is working on this. And again, at the Simons program, I think there's a whole workshop where there's lots of Markovian dynamics or even non-Markovian dynamics together with game. So there's always been that game theory melded with dynamics. But now if you bring in learning, and so yeah, as an older person, I look at that, I go, oh my God, that's just way too much to think about. But again, if you're younger, you say, wow, what a great opportunity. And that absolutely, I do believe there's a huge opportunities there. What I usually look for in that is it starts to get really more and more complicated. You got the Markovian plus this, and I say, is there going to be actual a simplification because we went to the Markovian or to the dynamical situation? Is there a mean field thing? Is there something that actually is going to collapse all that complexity? If there is, I'm ready to go after it. If it's just going to get more and more complicated, then no. But anyway, that's my own perspective.
Yeah. I guess I have one follow-up question regarding Professor Srikanth's question, and I have another question. So the one that is follow-up is, for example, in like continuous time dynamics or the engineering systems that has continuous space, network structure, and all these Markovian or even non-Markovian state transition. Do you think like this regret still being the suitable metric for analysis, or it is like stability type of analysis of such system?
Yeah, no, that's a fantastic question. And again, it's so broad and open. I may be able to say a little more concrete, but it just everyone should be thinking about it. Really, that's a great question. Short answer is no. Regret is not the end of the world, but it's not such a terrible notion. But just remember what regret is. The standard regret is that I've gone through some dynamical process. I look backwards and I say, in retrospect, I should have done this action. But I don't allow myself to look back and say I should have done this sequence. That's known to be hopeless.
Right.
And I don't even let myself to look back and say I should have done this little subsequence or something. Now, there are extended notions of regret, like swap regret and all that get a little bit more rich. But basically, when you define regret, you're defining an oracle, and relative to that oracle, you want to say something. And half the art is defining the right oracle such that some algorithm is actually capturing some aspect of some problem. And classical regret was basically just capturing the notion that when you do IID sampling by the law of large numbers, there's a square root of t factor, and regret can kind of capture that. The oracle can capture that looking back in retrospect, whereas the naive myopic algorithm cannot. And so it really captured that notion. But that one notion of regret is focused on that particular regime. Other notions of regret will be necessary, and people know this, for other regimes. And I think especially when you put it together with game theory, as you know, the no regret algorithms were developed kind of independent of game theory, but when they were applied to game theory, eventually people realized it was Blackwell's approachability idea and hiding. What you're doing is making a very strong worst case assumption that I'm just choosing actions and somebody out there is doing something.
Yeah, so that's more closely related to the coarse correlated equilibrium.
That's right. You
right,
converge to coarse correlated equilibrium in that case. That's right. Yeah, but the idea that dynamics converge to something game theoretically meaningful,
right,
it is great. But why use no regret dynamics? There is kind of the point. There's other kind of regret like dynamics which will converge to other sorts of things, which maybe if you're doing cooperative game theory, you want to converge to other kind of things. You don't want to converge
other equilibrium concepts.
Other equilibrium concepts, and what are the appropriate dynamics and why. And so regret just has this beautiful property that you have a smart oracle and allows you to do mathematics around that oracle somehow. Whereas just classical optimization, there was kind of no oracle. And so it allows you to bring in exploration. And so I love it. I would not throw it out as a concept, but the classical regret notion is extremely limited for good reasons, and we, other forms of regret will be necessary.
Yeah, thank you. I actually have another question if you still have a bit of time.
I'm fine, yeah.
Thank you. So in a lot of economy study for mechanism design contract theory, one big emphasis is the information asymmetry. Right.
Yeah.
So the principle, in mechanism design is the agents that have private knowledge of their preferences in contract theory, it's also like the moral hazard type of thing is like the contract designer cannot know about this.
Right.
As well as like you talked about this comparison between centralized versus decentralized analysis. Like the traditional machine learning gives a centralized platform a lot of information power. So I wonder, like, through this new decentralized learning, how is this information asymmetry is it being washed out, or is it still part of it still remaining? So a lot of issues in mechanism design and contract theory, like moral hazard, do you think it is still going to be relevant after learning?
Great question again, a very pregnant with possibility question. The short answer is yes, moral hazard is absolutely relevant. I mean, you know, the general way to think about this is that I'm in a decentralized setting, you know, this planetary scale setting, and there is some information over there that would be useful if it was over here, right? And the strategic part comes in because that information over there is possessed by somebody who may not find it in their interest to allow that information to be transmitted. But if they start to see it's a little bit in their interest, they'll allow a little bit of it to be transmitted. Okay, and so you need to sort of, the classical mechanism design and contract theory was kind of like try to get them to reveal everything.
Right.
And that's too stringent. So you want them to reveal something and they get a gain in return. And so, you know, things also like, you know, privacy. I don't want to have it be that you give me all your data or nothing. And so differential privacy is like kind of a knob you can turn to allow people to sort of express that I'll give you a little bit, but I expect something in return. Okay, and so, but these information asymmetries is that you possess something I don't possess, and I'd like to get you to do something. That's very much part of this. I should say, yeah, you're absolutely right that there's some decentralized elements when I talk, but there's a lot of centralized elements when I talk. And ideally, I'd move away as much as possible from the centralized elements, but sometimes that becomes hard. And again, I'm okay with it becoming hard if somehow that leads to something even better. And I do think that that's a good example. Decentralized can be better and easier to work with. But you're absolutely right. At that point, then you got to rethink your moral hazard kind of issues about how do I do that in a completely decentralized paradigm? How does, you know, how do I build mechanisms that allow that to happen? So I don't have much more to say about it, but, you know, absolutely important. Yeah, so, you know, almost all these concepts were already around in the 50s. It's kind of amazing. You know, Ken Arrow, David Blackwell, et cetera, they were already talking about this. And they really did develop approachability of David Blackwell. If you haven't read his 12-page paper on that, students, go read that. It's like, you know, it is almost all the no regret algorithms are examples of that. And he thought of that in 1952. And so those somehow the fields broke apart because they were so hard to do the tangle that people did all the separate, you know, computer scientists worked on no uncertainty. You know, EE people worked on linear systems, you know, statisticians worked on sampling and so on. But it's putting it all together. And economists were kind of left out of a lot of this. They kind of interacted with, you know, time series and analysts and so on, and some algorithm stuff, but they really need to be brought back in. And so all those concepts are actually should be part of our vocabulary.
Yeah. Thank you. This is truly inspiring. And we're already over time, so we're going to conclude here. Thanks, Professor Jordan, for the fantastic talk, and thanks for everyone for coming to this session.
All right, thanks everybody.
Thank you. Thank you, Srikant.